Okay, so we are going to solve some problems based upon yesterday's class. Okay, so let's begin. So let us see this first problem. Flow of 10 raised to 7 electrons per second in a conducting wire constitutes a current of. So this is very simple problem, right? So we have 10 raised to 7 electrons, okay, per second. So what is current? This charge flowing through some area per unit time. Okay, so it is, we can say, number of electrons multiplied by E is the charge. Okay, so we have number of electrons flowing per unit time. It's given, it is 10 raised to 7. So the 10 raised to 7 multiplied by E is the current. What is E? It is 1.6 multiplied by 10 raised to minus 19 coulombs, right? So this is current. 10 raised to minus 19 plus 7 is 10 raised to minus 12. Okay, so it's 1.6 multiplied by 10 raised to minus 12 amperes. Okay, so this is a very simple question. Yeah, option A. Let's see next one. The resistance of a wire is R ohm if it is melted and stretched to n times its original length. Its new resistance will be. This is the question. So what will happen if you stretch a wire? Okay, if you melt it and stretch it to n times its original length. Okay, so in this case, see, suppose this is your original wire, or let me draw it here. This is suppose the original wire. Now, if you stretch it, so length will increase. Something will decrease, right? The area of cross section will decrease. Okay, so because you are stretching it, so that extra length, the extra material, it should come from somewhere. Okay, so it comes from the area of cross section. So if you stretch it to twice the length, the area of cross section will become half. Okay, so how do we know? So we can assume that the volume remains constant. Okay, volume of the wire remains constant. So what is volume of the wire? It is area times this area of cross section multiplied by length. So A1 L1 equals to A2 L2, we can say, and therefore A1 divided by A2 will be equal to L2 upon L1. Okay, and what is L2 divided by L1? It's N, right? So it is equal to N. Now we want new resistance. So new resistance will be R2. It will be equal to rho multiplied by L2 upon A2. Okay, original resistance is R1, which is rho multiplied by L1 upon A1. So new resistance will be R2, rho into L2 upon A2. So now what is L2 in terms of L1? N times. Okay, so it is rho multiplied by L2 is N times L1. And what is A2 in terms of A1? So A1 upon A2 is N. That means if you take A2 on other side, okay, so from here we get A2 is equal to A1 divided by N, right? If you take A2 on this side, N on this side, okay, it will be A1 upon N. So let's put that. What do we get? It is A1 divided by N. So this N goes to the numerator, right? So we have rho multiplied by L1 upon A1 multiplied by N square. So this N square multiplied by R1. Okay, so R2 is equal to N square times R. Right? So we can remember this as a general result. What will happen to the resistance? Resistance will become N square. Okay, resistance will become N square times the original resistance, right? So see, for an example, this question has been repeated. many times. That's why I'm asking you to memorize this. Okay. So a wire of resistance 4 ohm is stretched twice its original length. Okay, so here N is equal to 2. The resistance of stretched wire would be, what's the answer? R2 is N square times R1. Okay, so it is N square is 4, 4 multiplied by R1 is 4, it is 16 ohms. Right, option B. Next question, a wire of certain material is stretched slowly by 10%, its new resistance and specific resistance become respectively. So can you tell? It will remain constant, right? You're not changing the material, okay? You're not changing the material, you're just changing the length. You're not changing the temperature also, right? So specific resistance will remain same, okay? And therefore, now R2 is equal to N square times R1, you can say. What is N here? So it is stretched by 10%, okay? Its length is stretched by 10%. So you can say L2 upon L1 is equal to, if L1 was 100, L2 will be equal to what? 110, okay? 100 plus 10, right? So it is 1.1 if you divide it. L2 upon L1 is 1.1. That means N is equal to 1.1. What is its square? 1.21. So R2 will be equal to 1.21 times R1. Option D. Next question. The electric resistance of a certain wire of iron is R. Its length and radius are both doubled. Okay, so this is not same as that of stretching of a wire. Okay, so now length and radius are both doubled. So you are putting some extra material here. The resistance will be doubled and the specific resistance will be half. The resistance will be half and the specific resistance, see, first of all, there will be no change in specific resistance. Okay, so there is only one option, I guess. No, there are two options. Specific resistance remains unchanged. Specific resistance, okay, resistance and specific resistance will both remain unchanged. So this thing we have to check. It's either option B or option D, because in other options they are saying specific resistance will change. Okay, so what's happening? Length is doubled, radius is doubled. So resistance is directly proportional to the length, inversely proportional to area of cross section. Okay, so area of cross section is equal to pi r square. So we can say it is inversely proportional to r square because pi is constant. So if you increase length, right, length is made twice L, area of cross section is made twice r. Okay, this is some constant and R2 will be equal to that constant multiplied by 2L divided by 2R square. So that is 2 divided by 4, okay, or 1 by 2. It will become half of R. So it's option B. Let's see next question. 6-volt battery is connected to the terminals of a 3-meter long wire of uniform thickness and resistance of 100 ohm. Okay, a 6-volt battery is connected to terminals of 3-meter long wire of uniform thickness and resistance of 100 ohms. Okay, the difference of potential between 2 points on wire separated by distance of 50 centimeter will be. So this is the question. So see, we have a 3-meter long wire. This is 3-meter long, and potential difference between the terminals of this wire is how much? It is 6 volt. Okay, So potential difference is 6 volts. V is equal to, now we can say V is equal to I times R. Okay, it is 6 volts, which is equal to 6 volts. So we can say I is equal to whatever is V. Okay, it's 6 divided by R, right? Now, if you consider wire, R is also given actually. Okay, so now you consider wire having length equal to 50 centimeters. Okay, this is 50 centimeters, right? So we know that resistance is directly proportional to length. Okay, so if we call the total resistance as R1, okay, how much would be the resistance of this one? Its resistance will be, suppose R2, it will be directly proportional to length. Okay, so R1 is equal to, I can say, some constant multiplied by L1. R2 is equal to same constant multiplied by L2. So if you take the ratio of R2 to R1, what will you get? You get that resistance is equal to what? R2 upon R1 is equal to what? L2 upon L1. So this is 50 centimeters or 0.5 meters divided by, you have 3 meters, right? 3 meters. So 0.5 upon 3 is 1 by 6. Okay. So R2 is equal to 1/6 of R1. Okay. So this is equal to 1/6 of R1. So V is equal to I into R. Same current is flowing through this section also. Okay. So resistance becomes half, not half, 1/6. The potential difference will become what? 1/6. So it is 1 volt, right? It is equal to 1 volt. Option C. Got it? Yes, no? 3 copper wires of length and cross-sectional areas are L, A, 12, A by 2 and L by 2, 2A. Resistance is minimum in. So we have to check this, right? Okay. So resistance for first one. Okay, let's call it R1 equals to some constant L upon A. R2 equals to same constant 2 times L divided by A by 2. So this will go into the numerator. It is C multiplied by 4. Okay, 4C times L by A. And R3 is equal to what? C multiplied by L by 2 divided by 2A. So this will be 1/4. Okay. So R1 is CL by A, R2 is 4C L by A, and R3 is 1/4. Yeah, it's option wire of cross sectional area 2A. Right. So option A. Okay. Let's see next question. A wire 50 centimeter long and 1 mm square in cross section carries a current of 4 amperes when connected to a 2-volt battery. The resistivity, this is very simple question, right? Wire 50 centimeter long and 1 mm square in cross section carries a current of 4 amperes when connected to 2-volt battery. The resistivity of wire is, this is the question. So yeah, V is equal to Ri, we can say R is equal to V upon I. So that's given. Okay, V is 2, A is 4. Okay, so it is 0.5 ohms. Okay, then R is equal to rho times L upon A, and it's equal to 0.5 ohms. Take A and L on the other side, so we get rho is equal to 0.5 multiplied by A upon L, so which is A is 1 mm square. We have to convert that to meters. 1 multiplied by 10 raised to, this mm square, right? So 1 mm is 10 raised to minus 3 meters, and we have square of that, not minus 2, minus 3 square. Okay, 1 mm square is 1 multiplied by 10 raised to minus 3 square meter square. Okay, then length is 50 centimeter, that too we have to convert it meters, so it is 50 multiplied by 10 raised to minus 2. So now there is nothing. Okay, it is 10 raised to minus 6. Minus 6 plus 2 is 10 raised to minus 4. And if we make this 50, so it will be another minus 2, right? So 0.5 can be written as 50 multiplied by 10 raised to minus 2. Multiplied by, I'm sorry, we have 10 raised to minus 4. Okay, divided by we have 50. So this thing gets cancelled out. This 10 raised to minus 6 is the answer. Option B. The masses of the wires of copper is in the ratio of 1 is to 3 is to 5, and their lengths are in the ratio of 5 is to 3 is to 1. The ratio of their electric resistance is, this is the question. Okay, so masses are in the ratio of 1 is to 3 is to 5, and lengths are in the ratio of 5 is to 3 is to 1. Okay, all right. So this is, yeah. Okay, so we can say mass is equal to density multiplied by volume. I will use D for density. So M is equal to density multiplied by volume. And what is volume? Area times length. Okay. So now if we want areas, we can find it from here. Okay. So area is equal to what? Mass divided by density multiplied by L. Okay. And density will be same. Okay. Density, because it is same material, it's copper. So density would be same. So area is mass divided by density multiplied by length. Okay, D is density. Remember, this is density, not diameter. So now it's simple, right? So what is resistance? It's directly proportional to length, inversely proportional to area. So let's find out for first. Or let's find out the formula. It is R is equal to rho L upon A, and A is what? M upon DL, right? M upon DL. So it is rho multiplied by L divided by A, which is M upon DL. So we can move that D times L in numerator. Okay. It is rho times D L square upon M. This is the formula now, right? Rho times D L square upon M. So we can find out the ratios now. So R1 is to R2 is to R3 would be equal to what? So rho is a constant, D is a constant. It is just ratio of L square upon M. So what are the, okay, so it is L1 square divided by M1 is to L2 square divided by M2 is to L3 square divided by M3, right? And what is ratio of the lengths? Ratio of lengths is 5 is to 3 is to 1. Okay, and we have square of that, so it will be 25, right? I'm just writing length, so 25 is to, okay, I'm just writing numerator, 3 is to 1, so 9 is to 1, and ratio of masses is 1 is to 3 is to 5. We can write it down directly, so 1 is to 3 is to 5. So what is the answer? It's 25 is to 9 by 3, which is 3 is to 1 by 5. Or we can multiply whole thing by 5, which will give us 125 is to 15 is to 1. Yeah, it's option D. Yeah, good. It's option D. Let's move on to the next question. Copper and silicon is cooled from 300 Kelvin to 60 Kelvin. The specific resistance decreases in copper but increases in silicon. Increases in copper but decreases in silicon. Increases in both, decreases in both. Tell me, increases in copper but decreases in silicon. They are cooled. Copper is a metal, right? Silicon is semiconductor. Okay. So for semiconductors, what happens if they are heated? The resistance will go down. Okay, resistance will decrease. Resistivity will decrease. If they are cooled, their resistivity will increase. For metals, if they are heated, the resistivity will increase. If they are cooled, the resistivity will decrease. Okay, so it is option. They are cooled, so for copper it will decrease, right? Option A, decreases in copper but increases in silicon. Let us see next question. Specific resistance of a conductor increases with increase in temperature, increase in cross section area, increase in cross section, and decrease in length, decrease in cross sectional area. So last three options are irrelevant. Okay, the specific resistance doesn't change with change in cross section or length. It is property of material. It only changes with temperature. So it is option A. So suppose you increase the temperature. Okay, if you increase the temperature, then what will happen? For metals, the resistance will increase, right? For metals, the resistance will increase. So suppose R naught is resistance at T equals to 0 degrees Celsius, we can say. R at temperature T is resistance at temperature, it is resistance at temperature T. Okay, what change in resistance? To change in resistance is RT minus R naught, and it will be directly proportional to the change in temperature. Okay, it will be directly proportional to the change in temperature. So I can say change in temperature is delta T, okay, which is T minus T0, we can say. Instead of 0 degrees Celsius, let's take T0. So this RT minus R naught would be directly proportional to delta T, right? And RT minus R naught, which is change in resistance, will be directly proportional to the original resistance. Can we say it is directly proportional to the original resistance? Okay, we can say, right? Because if original resistance is 5, let's suppose 10 ohm, and then increment is 1 ohm. So if original resistance was 20 ohms, there will be some percentage increment which would be equal. Okay, so if original resistance is 20, it will increase by 2. Okay, this is just an example. So we can say RT minus R naught is proportional to R naught and delta T. So we can write that RT minus R naught is proportional to R naught times delta T. Okay, then there will be a proportionality constant. Okay, RT minus R naught is equal to constant is alpha. Okay, so it is alpha R naught times delta T, and you can move that R naught on the other side. So you get RT is equal to R naught plus alpha R naught times delta T, or you can take R naught common. So RT is equal to R naught multiplied by 1 plus alpha delta T. This is the formula. Okay, resistance at temperature T is equal to resistance at 0 degrees Celsius multiplied by 1 plus alpha delta T. This is considering that there is linear relation between change in temperature and change in resistance. Okay, and this alpha, the constant of proportionality, it is known as the resistance temperature coefficient or temperature coefficient of resistance. Temperature coefficient of resistance. Okay, so now the thing is, for some materials it is positive, for some materials it is negative. Okay, so it is positive for all metals. It is negative for semiconductors and insulators. It is negative for semiconductors and insulators. So reason we had discussed on yesterday, right? So what happens? So we can write resistivity. Formula for resistivity, it is m divided by Ne squared tau. Okay. So for metals, what happens? That as temperature increases, the number of collisions happening between electrons and ions or atoms inside the metal, it will increase because velocities will increase. Wiggling of atoms or ions will also increase, right? So therefore more collisions will happen. So time between two successive collisions, the average time, which is tau, will decrease. So if tau decreases, what happens? Resistance will increase. Sorry, resistivity will increase. So therefore, in case of metals, the resistance increases in general with respect to temperature. So alpha is positive. Alpha is positive for metals. Okay. Now what happens in case of semiconductors and insulators? So this thing is true. Tau will decrease. Okay, the electrons, they will move faster. Atoms will wiggle faster, and that's why there will be more collisions. But in case of insulators and semiconductors, initially no electrons are available for conduction. Okay, and as you increase the temperature, what happens? Now electrons gain some energy to come out of their respective bonds, you can say, to come out of outermost orbits in case of semiconductors, and come out of the bonds, covalent bonds, okay, in case of insulators, right? So more number of electrons will be available for conduction. Okay, in case of semiconductors, it is electrons as well as holes, right? So more number of electrons will be available for conduction. So tau decreases and increases. Now there is competition between these two. So whatever happens faster, okay. So if tau decreases faster, then resistivity will increase. Okay, because it is inversely proportional. But here n increases faster compared to the decrement of tau, and that's why resistivity decreases as you increase the temperature. Okay, so alpha is negative for semiconductors and insulators. So some materials have positive temperature coefficient. It is known as PTC, positive temperature coefficient of resistance. Some have negative temperature coefficient of resistance. Okay, so this is for metals. This is for semiconductors. Okay, and insulators. Okay, so the graph of resistance versus temperature for metals will look something like this, right? For semiconductors and insulators, it will look something like this. Okay, it's resistance versus temperature because they have negative temperature coefficient. And for some materials, the graph will look, okay, for substances like mica, nichrome, the resistance doesn't change much. The resistance doesn't change much with respect to increment in temperature. Okay, so it is like this for metals, like this for semiconductors and insulators, and for some materials, mica, nichrome, up to some extent we can say carbon also. Okay, carbon also, it's not that steep. Okay, so resistance versus temperature graph is like this. So they have very low temperature coefficient of resistance. These kind of materials are used mostly to make the electric devices because they are faithful. Okay, their resistance will not change much with respect to increment in temperature. Got it? Yes, no? All right. So let's see next. Okay, this problem only. The solids which have the negative temperature coefficient of resistance are, tell me. Yeah. It's option D, insulators and semiconductors. Okay, next one. Which of the following graph represents the variation of resistivity with temperature for copper? Okay, 1, 2, 3, 4. Tell me. Option C. Right. Option C. Next one. From the graph between current and voltage V is shown, identify the portion corresponding to negative resistance. This is simple. Is it A? Yeah. So as you increase the voltage, the current is decreasing. Okay. So it's option A. Right. Let's see next question. The mean free path of electrons in metal is 4 multiplied by 10 raised to minus 8 meters. The electric field which can give on an average 2 electron volt energy to an electron in the metal will be in units. What is mean free path? So what is free path basically? It is the path traveled by an electron between two successive collisions. Okay, the distance covered by an electron between two successive collisions is mean free path. Not mean free path, it is free path. So the average distance covered by an electron between two successive collisions. So maybe when it collides for the first time, okay, the distance is something. Let's call it S1. For second time, it's S2. Okay, between first and second collision, it is S2. Then it is S3. So average of those distances is suppose S. Okay, so on an average, we can say electron gets this much distance to travel, okay, before it collides. Okay, so on an average, electron gets distance equal to mean free path to travel between two collisions. Okay? So electric field is given, electric field which can give an average of 2 electron volts energy to an electron. Okay, so electric field is asked actually which can give 2 electron volts of energy. So this is electron volt is unit of energy. And what is electron volt? So it is energy gained by an electron when it is moved by 1 volt, that is 1 electron volt. Okay, so how much is 1 electron volt? 1 electron volt is energy gained by electron when it moves through 1 volt of potential difference. So it is equal to charge on electron. Okay, charge on electron multiplied by 1. Okay, because potential difference is 1, right? We can say charge on electron is E multiplied by 1. Okay, 1.6 multiplied by, if we want to write it down into, so it is E multiplied by 1, or we can say 1.6 multiplied by 10 raised to minus 19. This is charge on electron. Okay, and we want energy, so it is joules. 1 electron volt is 1.6 multiplied by 10 raised to minus 19 joule. Got it? So now question is, the electric field which can give on an average 2 electron volt energy to an electron. So now so suppose some electric field is there, okay, and electron moves through that electric field. So this is the electric field, suppose. Okay, E is the electric field. So it moves through some distance. So distance is equal to how much? It is mean free path 4 into 10 raised to minus 8 meters. Okay, so we can say there will be some work done. Work done will be equal to what? The electric field, sorry, it will be force multiplied by displacement. Okay, force multiplied by displacement. So how much is force on electron in an electric field? Force is equal to what? It is E multiplied by E. Okay, charge on electron multiplied by electric field. Okay, so work done is equal to charge on electron multiplied by electric field multiplied by S, the displacement. And it is given that it is equal to 2 electron volts. Okay, it is equal to 2 electron volts. That means it is energy gained by electron when it moves through how much of potential difference? 2 volts, right? So it is E, this is charge on electron, right, multiplied by 2 volts. Okay, so this I have done because E and E will get cancelled out. Okay, so E is equal to just 2 divided by S. Okay, E is equal to, we get 2 divided by S, and S is 4 multiplied by 10 raised to minus 8. We can substitute that. So E is equal to 2 upon S, 2 upon 4 multiplied by 10 raised to minus 8. That is half, and you can move 10 raised to minus 8 to numerator, which becomes 10 raised to plus 8. 0.5 multiplied by 10 raised to plus 8, or you can say 5 multiplied by 10 raised to 7. Okay, volts per meter. So this is the answer, option C. R is equal to this thing 16 plus minus 1 ohm, L is equal to 5 plus minus 0.1 mm, and D is equal to 10 plus minus 0.5 mm. Find error in calculation of resistivity. Okay, find error in calculation of resistivity. So we know R is equal to what? Rho times L upon A. Okay, resistivity we can write it as R times A divided by L, right? So it's directly proportional to R, directly proportional to area. So this is diameter. Okay, so area is directly proportional to diameter. We can say rho is proportional to R, area is proportional to what? Diameter square. Okay, so we have rho proportional to R d square upon L, and we want error in calculation of resistivity. We know that from dimensions, right? So delta rho divided by rho will be equal to delta R upon R, okay, plus 2 times delta D divided by D plus delta L upon L. So whatever it is, so it is 1 upon 1 divided by 65 plus 2 multiplied by delta D upon D. So it is 2 times 0.5 divided by 10 plus how much? It is 0.1 divided by 5. Okay, So this is, so we can multiply it by 100 because we want percentage resistivity. Okay, so percentage error in resistivity. So 100 divided by 65, okay, which is 20 divided by, okay, this can be written as 13 times 5, and this is 20 times 5. So 20 divided by 13 plus we have I'm sorry, this is 1. 100 divided by 10 is 10 plus we have 100 divided by, sorry, 100 multiplied by 0.1 is 10. 10 upon 5 is 2. 10 plus 2 is 12, and this will be 1 point something. Okay, it will be 13. Let's see next question. The resistance RT of a conductor varies with temperature T as shown in the figure. If the variation is represented by this thing, okay, it is not linear proportion, it is RT equals to R naught 1 plus alpha T plus beta T square. Then alpha and beta both are negative, alpha is positive, beta is negative, alpha and beta both are positive, alpha is negative and beta is positive. Tell me. Alpha and beta both are positive. Good. Okay, because we have seen such kind of a curve. I mean, this is what? A parabola. Okay, and equation of parabola is what? Equation of parabola is, general equation is y equals to ax plus bx square, right? Where a and b both are positive. Let's see next one. A conducting wire of cross-sectional area 1 centimeter square has 3 multiplied by 10 raised to 23 charge carriers per meter cube. Sorry. If wire carries a current of 24 milliampere, then drift velocity of carriers is. Okay, what is formula of drift velocity? We are, okay, current is given. So we want current in terms of drift velocity, right? So I is equal to NEA VD is the formula. So everything is given. Yeah, area is given. Then charge carriers per meter cube. That means N is given and current is given. So this is straightforward. VD is equal to I divided by NEA. Okay. Then there is just calculation. So this is a problem actually. There are a lot of calculations. Current is 24 milliamperes. 24 multiplied by 10 raised to minus 3. N is, okay, this seems simple. 3 times 10 raised to 23 multiplied by charge on electron 1.6 into 10 raised to minus 19. And what else? Area is 1 centimeter square. So which is 10 raised to minus 4 meter square, right? 24 divided by 3 is 8. So you have 8 divided by 1.6. That's good. Okay, so 16 divided by 8 is 2. So we have 1.6. So this will be 0.2, right? Or 0.2 in denominator, or we can say this is 80 divided by 16. Okay, 16 5s are 80. Multiplied by, take that 10 raised to 23 minus 19 is 4, and this minus 4, it gets cancelled. Okay, so we are just left with 10 raised to minus 3. So it is 5 multiplied by 10 raised to minus 3 meters per second. Okay, it's option C. Temperature coefficient of resistance of a wire is 0.00125 per degree Celsius. At 300 Kelvin temperature, its resistance is 1 ohm. The resistance of wire will be 2 ohm at. This is the question. Okay. So RT is equal to R naught multiplied by 1 plus delta T. Right. So this is the formula. So I can say R1 is equal to R naught. R naught is the temperature at 0 degrees Celsius. Okay. Multiplied by 1 plus delta T. What is 0 degrees Celsius? 0 degrees Celsius is 273 Kelvin. Right. So R naught is at 273 Kelvin. So what will be delta T for 300 kelvins? Is 300 minus 273. Right. 300 minus 273. Okay. Delta T1 we can say is 300 minus 273, which is 27 degrees Celsius. Okay. This R0, R1 is R0 1 plus delta T is 27. And R2 will be equal to R0 multiplied by 1 plus something, some delta T, we don't know. Okay, that we have to find out. Then we can divide this. Oh, it is alpha delta T, right? I made a mistake here. It is equal to R naught multiplied by 1 plus alpha delta T. So it is 27 alpha here. Here it will be some delta T times alpha. Okay. So we can divide second by 1 or first by second. So this R naught will get cancelled. This is 1 by 2. So we can say 1 by 2 is equal to 1 plus 27 alpha divided by 1 plus delta T times alpha. Okay. So that is 2 multiplied by 1 plus 27 alpha is equal to 1 plus alpha is also given. Okay, alpha is also given. So we can put that. All right. So 2 is 2 times 1 plus 27 alpha is equal to 1 plus delta T times alpha. Okay. So 0.00125 per degree Celsius. Okay. So we can say it is 125 multiplied by 10 raised to minus 5. Okay. So this is 2 plus 54 alpha is equal to 1 plus delta T alpha. Then we can take that 1 on other side. So it will be 1 plus 54 alpha equals to delta T times alpha, and therefore it implies that delta T is equal to 1 plus 54 alpha divided by what? Alpha only. Okay. So now we can substitute for alpha. Yeah, good. Delta T is equal to 1 plus 54 multiplied by 125 into 10 raised to minus 5. This is our alpha. Okay, 125 multiplied by 10 raised to minus 5, and in denominator 125 times 10 raised to minus 5. Let us see next question. If resistivity of copper is 1.72 multiplied by 10 raised to minus 8 ohm meter, and number of free electrons in copper is this much, find the mobility. Okay, find the mobility. The number of free electrons, this is number of free electrons per unit volume. Okay. So now we know resistivity is given by which formula? It is m divided by n e square tau. Okay. And mobility. Okay, we want to find out mobility. So we know that what is mobility? Where does it come from? So current density J is equal to what? Sorry, mobility. We have Vd equals to mobility mu multiplied by electric field, right? So drift velocity is equal to mobility multiplied by electric field. Okay. So then we have resistivity. Yeah. So drift velocity, if we write, it is n. Sorry, not n. Drift velocity is given by what? E into E multiplied by tau upon m. Okay. This is drift velocity. It is mu times E. So if you cancel it out, cancel out E, you get mobility. Mobility equals to E times tau divided by m. Okay. So what is given? So we are given with resistivity of copper. So resistivity we know, and number of free electrons is given, which is 8.5 multiplied by 10 raised to 28. Okay. And mobility is asked. So I can say that E times tau is equal to mu times m, right? So instead of dividing, I can put E times tau is equal to mu times m, because I'm not given with the tau, right? We don't know what is tau. We can substitute it here. Okay, so we get m upon n multiplied by E, and so I will write this E square as E times E. Okay, so we have E times E multiplied by tau, and what is E times tau? It is mu multiplied by m. Okay, so this m and m will get cancelled, so we are just left with n E mu. Okay, so we get formula for mobility in terms of resistivity here. Okay, so it is equal to 1 upon n E rho, right? Because this m and m will get cancelled out. Yeah, so then we can substitute all the values. Okay, so it is 1 upon 8.5 multiplied by 10 raised to 28. Oh, so many calculations. Then 1.6 multiplied by 10 raised to minus 19. Then multiplied by, we have rho, which is 1.72 multiplied by 10 raised to minus 8. Okay, so this is 10 raised to minus 19 minus 8 will be minus 27. So minus 27, and this is 28. Okay, so it will be roughly 10, we can say 10 times 8.5. So we can roughly say it's 1 by 100. Okay, of the order of 1 by 100. So is it there?